Okay, let's begin. First off, here's the homework. I am going to give you a worksheet that covers up to here. Okay, that looks like this. Let's see. That one. That has the graphs that you'll need for your homework. So you'll be graphing. You'll be doing a lot of graphing. So I'll give you this up to just the first and second page. If you want, you can, starting at 39, you can print this more or do it on graph paper or something. And I just don't have enough paper to print both pages for you. And then there's a few review problems at the end. But I'll pass that out so you can, or go online and you can print it out yourself. Okay. So there's that. I'm going to start off actually with a little bit of review. As you guys know, I've been trying to relate all the graphs together that we've looked at. So we've looked at parabolas. I mean, we looked at absolute value a long time ago, and we said, well, this value does this to the graph. This value on the inside of the absolute value moves the graph from left to right, and so on. Okay, and we did that with square roots, which are half of a parabola, remember? And we saw the same thing, only this value this time, it was there, but making this value bigger actually made it wider, as opposed to the quadratic. When you make this value bigger, it makes it skinnier. So, but they still had this value that was there that did something. So as we're doing anything that's new graphing, and we actually have a few more graphs to go through. I mean, we saw this in cubics when we had these types of graphs that were written a certain way. It just moves the graphs wider, skinnier, up and down, left and right, that kind of thing. So anytime we come to a new graph, you want to think along the same lines. You don't want to start all over and say, oh, this is going to be weird. This is going to. I mean, if you can catch the pattern, the mathematical pattern, they're pretty much all these behave identically. Even these crazy step functions, they still move left and right, up and down in the same way. Yeah, there's some differences, but there's more similarities. So as we're doing this, I want you to think that way as well. Okay. Yeah, I can make A bigger, and it bends in a certain way. When it makes it negative, it looks this way. Okay. But when I have this number on the bottom, and I move that number, it does the same thing it always has. Okay, this time not an absolute value, not being squared, but this time it's being divided by. It moves the graph from left to right. And of course, if you just have a number on the outside, that's like a vertical shift. Okay. So more similarities than differences, right? But let's look at the differences. First of all, look at the graphs. They seem to be approaching numbers in both directions, meaning if I'm going down this way, I follow the graph, it seems to get closer and closer to 0, but never actually touches 0. Okay? And same thing here. If I follow it to the left, it gets higher and higher and higher and higher, going up to infinity, but it looks like it never actually gets, even if I go up here more and more and more, it never actually touches the axis. It just gets closer and closer and closer. Okay? And then magically, for some reason, as it goes higher and higher, it just jumps way down here to the bottom. Okay? And we'll look at why that is in a minute. Okay, and then it's same thing on this side. It kept on approaching, get real close to 0. It does the same thing over here. It gets real close to 0, never actually touches. But depending on what the numbers are, it could get real close to 1 or 2 or 3 or 4. So the question is, for today, is how do you know where this big magical shift is going to happen? Okay? How do you know where this is going to happen? Do that. How do you know it's going to go up and up and up and all of a sudden jump way down here? And more importantly, why does it do that? Okay? Why does this occur? Okay? So we're going to know how to calculate, figure out how to calculate all of this stuff. Alright, so here, let's go here. Short answer is, if I can grab this, there we go. If I move this to, I'm going to make this equal to 3. Okay, so h is equal to 3. So I have x minus 3 on the bottom. What happens when I plug in 3 right here? What happens when I plug in 3 in the bottom here? What do you get on the bottom? 0. And anything divided by 0 is what?
1.
Anything divided by 0 is... It does not exist. It's undefined. And that's why there is no graph at that point, because it's undefined. If the answer was 0, if I plugged in 3 and I got the answer as 0, there would be a point right here. Okay? There would be a point right there that the graph would be connected to. But there is no point on this line at 3 because it's impossible to divide by 0. So in short, if I ask you the question, how do I know where this phenomenon occurs? It's where you divide by 0 in the equation. So if I plug in 3 right here, I get 3 minus 3 on the bottom, which is 1 divided by 0. That's undefined. That's how I know where this is going to occur. Or I'm not going to have a value of the graph. And it's where you're going to see this jump, where it goes up and up and up, and then all of a sudden it goes way down here. Okay, because there is no value at positive 3. It does not exist. Okay. The name we call this is called a vertical asymptote. Vertical asymptote. It's where it jumps. Think of this as the equivalent of the vertex of a parabola. It's kind of like your center. And when we're graphing, you want to find this value first, kind of like how you found the vertex first, and then you pick numbers to the left and numbers to the right, just like you did with graphing parabolas, or even the cubics, or absolute value. But we have to know how to find this value first, and then pick numbers to the left, pick numbers to the right of it. You don't want to just pick 0 and pick some negatives and pick some positives, as you know, because that doesn't work in the parabolas as well. Alright, so, and to know where this happens is to know where it divides by 0. Where do you divide by 0? What values, when you plug in, give you 0 in the denominator? That's it. So if you can answer those questions, you'll be fine for the homework. But you have to know that this occurs when you're undefined, when you're dividing by 0. So here we go. All right. So real fast, let's just review looking at these values and looking at the denominator and what values give you 0 on the bottom. Not difficult, but still worth reviewing. There we go. Get these out of the way right now. Okay, so for instance here, what value will give you 0 on the bottom? Yeah, m equals 5. So I know, that's kind of like the vertex, I know before I even start anything else that I'm going to have this vertical asymptote right here. And the graph may look like this, okay, or it could look like, this. I don't know much other than that for sure right here there's not going to be any values because that's where it's undefined. If I plug in 5 right here on the top and bottom, I'll get some number divided by 0, which is undefined, and you can't graph something that's undefined. So we just put this dotted vertical line to show that this whole vertical line is undefined. All values of 5 are undefined. What value here of n will make it undefined? -2. So I know that at -2 I'll have this vertical line, and then stuff will happen on the left and right. Okay. Over here, if you simplified everything, 28 goes into 56 2 times, I believe. This will simplify to 1 over 2k. Okay. And k could not equal 0. So on this one, the asymptote will actually be right there. And it'll look something like this. So, kind of like a parabola, that these right here, this is not vertical right here. This is not straight up and down. So you remember a parabola looks like this. It keeps on going outwards and outwards and outwards. At no point does it look like a U, that it's straight up and down. That's not a parabola. Same thing here. It just keeps getting closer and closer and closer to that asymptote, but never actually gets to it. Okay, so some properties of parabolas in here. Alright. So, what do we want to do first? Let's just get to graphing. How about that? If you would work, that'd be very nice. Okay, so we have this word, this is the word asymptote. And we're talking about vertical at this point. Like here, this is the vertical asymptote. And again, it's the value that makes the denominator equal to 0. So, and I would say value or values, because there can be multiple vertical asymptotes. It's possible. These are rationals, yeah. Rational just means it's a fraction. This is rational means. So denominator of that fraction. So we're just looking right here. What value makes this equal to 0? 3. And that's why this dotted line is at 1, 2, x equals 3 on the x-axis at 3. That's all. It's where you cannot get a value because it's impossible to divide by 0. So we can plug in any other number and we'll get an answer. And there'll be a decimal probably. But when you plug in 3, there is no answer. It's not, the answer is not 0. There is no answer. Okay. Okay. There you go. And I'll go back to this other part and then this is the main thing. And consider this kind of like the vertex of rational functions. It's kind of like the center of where everything kind of starts and where everything's going on. Alright, so here, what is the vertical asymptote here? Positive 1, right? So I know, just to start off, on your graph, you got positive 1. And same thing, it's kind of like the middle of your graph here. It's going to be the middle of your table here. Plug in 1. And of course, if you actually show the work for it, you get 1 plus 1 over 1 minus 1, which equals 2 over 0. And you can say undefined, or you can put like VA for vertical asymptote. And then we're going to pick some numbers to the left and numbers to the right. Now, when you're picking numbers to the left and number right, you might remember with like the parabola, you kind of wanted to make them like mirror image like because the graph was mirror image. There's some of that properties here, but there's a danger into picking like only numbers really close to here. So if you only pick 0 and -1, you'd only get to see the graph from here to here. You get to see a very small piece of it. So try to stretch out your number choices on the left and right hand side. Pick an easy number like 0, but also -4 and -8. So you can really see what's going on the whole graph, not just right around the asymptote. Same thing on the other side. We can pick maybe 2, and then 4 and 8 as well. And that'll give us what's going on the entire graph, not just the little part right next to our vertical asymptote. Okay, now here comes the not so fun part. You just have to crank out all the decimals. So we'll have to take -8, plug it in, and do -8 plus 1 over -8 minus 1. That equals -7 over -9, and that's about positive 1.28. Okay? And convert to decimal so it's easier to graph, and you just have to go through and do them one by one. Okay? So go ahead and do that, and then we'll plot them together and see what it looks like, see what this graph looks like. Verify with people around you that you're getting the same decimals. We don't want any errors here. By the way, if I told you to do this, there's some of you that could pick up your calculator, have this whole chart completed in 20 seconds. Buying that one calculator I've been telling you to get from the beginning of the year, and then you'll pretty much be done. So if you have that calculator and you know how to use the table function, your homework's going to take about 15 minutes. If you don't, your homework might take about 45 minutes. So I still have half the year left. You might want to invest in one of those calculators that gives you a table, so it's much faster on the homework as well as on the tests. You wouldn't have to crank it out and do it one by one. If you guys like to have 15 extra minutes during a test, get a better calculator, okay? So it's worth the investment, I promise. So let's fix that. 0.77. Okay. So we've got -8 and 0.77. Okay, what's another one? What do we get for -4? 0.5, a half? Okay. And what do we get for, what's the next one? For 0? What do we get for 0? -1? Okay, plot that one. Here. Yep, 2. We don't put in the asymptote because that's undefined. So we'll go to 2, and we got 3. Okay. And we'll put in 4 and then 8. So for 4 we get 1.6. Okay. And for 5 or for 8 we get, what's that? 1.2? Okay. Yeah, okay. Good. And we know there's, yeah. So you can see this is what we get just from plotting. So we really need to know about that asymptote and where it is. It's very important. Without it, it's not going to help. So if I go over here, you can see it follows those dots quite nicely. Quite nicely it follows those. And remember, this is a dotted, undefined line at equals 1. And that's what you'll do for a majority of these. Find that vertical asymptote as it was a vertex, pick some numbers to the left, some numbers to the right. Okay. And again, if you have a calculator that does a table, you'll be finished with these really fast, like I hope you are. Alright. So, we got that. Okay, one that's slightly different. When possible, factor. So what is the top factor to? What does that factor to? So you might have to go over here and say what two numbers multiply to -5 and add to 4. And come up with your two numbers, which are 5 and -1. So we got x minus 1 and x plus 5. What do you notice that happens here? X plus 5's cancel. So here's the second type of problem I'm going to show you. What happens when something cancels? How does that alter the graph? Okay. We could just graph this, what's left over. And that'd be like y equals mx plus b. That'd be like a slope of 1 over 1 with a y-intercept of -1. That's just a straight line. Okay. But how does this canceling out business affect that graph? What does it do to it? Okay. So are there any vertical asymptotes here? Okay. Is there any number down here that, well, yeah, is there any number at the bottom at all that I could plug in and get a 0 on the bottom, knowing that these are cancel out? Is there anything left on the bottom? No. So there's no vertical asymptotes. No. You've never had them before because you've never had divided by x plus 5 or x minus 6. So if there's nothing left on the bottom, you have no vertical asymptote. So it's not something that from now on is always going to be there. It only exists when you're dividing by a variable. Okay. But in a sense, it still does something to the graph. So let's just go ahead and graph it as we would normally. Okay, we could use a t-chart here. I could just pick 0 and 4 and 6. And then also, let's go 2 and 7. I could do the work. Okay, x minus 1, so that's 6 minus 1, which is 5. 4 minus 1, which is 3, and so on. And get your graph. Let's see, 6, 5, 4, 3, and 0, -1. There's your y-intercept. 2, 1. Oh, I should pick some negatives, huh? I meant to pick some negatives. It's okay. Let's make that. That was -7. This would be -8. Yeah. -7, -8. Okay. And seemingly it looks like that we just get a nice graph that, like we always would, right? However, going back not to the one that we simplified, but to the original, is there anything that doesn't work in the original as far as makes it dividing by 0? What value here? -5. So the fact that it makes it a 0 on the bottom, we might say, oh, that's a vertical asymptote. It makes it a 0 on the bottom. But the fact that it cancels out means it's just what they call point discontinuity. Or in other words, at that value of -5, there's just a hole. There's an open space. Kind of like that if you graph like x is greater than 2 or something like that, and you graph that number line, open circle, pointing to the right. It's the same type of thing. It means that, well, 2 is not an answer, but everything bigger than 2 is. Here, everything is an answer except at -5. Okay? Because in the original problem, it still equals a 0 on the bottom. Even though it cancels out, on the original problem, it still is undefined. So we have two types of new mechanisms here. We have here where, well, it doesn't cancel out. Like x minus 1 didn't cancel out at all, and we got this vertical asymptote, and the graph went on to look. Hello. Oh no. Oh snap. I just lost everything, didn't I? Yeah. Well, the graph went on to look something like this. Okay. So we have this type of graph where nothing canceled and we have a vertical asymptote. And then we have here where it did cancel, therefore there was nothing left on the bottom, no vertical asymptote, but we have this hole where for the value that did cancel. So one that does cancel, one that does not, basically. The one that does not is a vertical line. The one that does cancel, like the x plus 5's cancel top and bottom, that's just an open circle at x axis. This is the x axis at -5. So two things going on. Now there can be both of these going on. You can have an equation that has a vertical asymptote and a hole. Okay? So these are the things you're always going to be looking at. First thing you're going to do is always factor. Factor the top, factor the bottom. Okay? Then you're going to consider the limitations of the domain. That means basically look for dividing by 0. You can't divide by 0. That's a domain restriction or limitation. And then, are there any holes? Meaning, given those restrictions, does anything cancel out? Are there any holes? Okay. This question is, cancels top and bottom. Okay, that's the question. Does anything cancel on the top and bottom? That's the hole. So here, x plus 5 canceled on top and bottom, so x equals -5 was the hole. And here, okay, that's anything left on the bottom. Anything left on the bottom. So values that make you divide by 0. Is there any values left over that make you divide by 0? And like this one, the bottom completely cancels out. There's nothing left on the bottom, so there's no value you can have that will divide by 0 because there's no variables on the bottom. So the first few questions on your homework, let me show you, ask you only that. You don't have to graph these yet. They just ask you, what are the vertical asymptotes and what are the holes? What values? Factor. So factor the first one. If nothing cancels, then those are the values that are the vertical asymptotes. When you get to like 15 and 16, you can see, maybe something cancels. Maybe x plus 3 cancels top and bottom. So you'll have one vertical asymptote and one hole. The vertical asymptote is the one that's left over, and that hole is the one that cancels. Alright. And then finally, we're not going to go through this all the way, but once again, you have to know how to factor this. What is the top factor to? Yeah, so x plus 1, x minus 1. What does the bottom cancel to? X minus 5, and x minus 1. So you're kind of expected to know how to factor these quickly. Notice they should take a matter of seconds, very quickly. And then, alright, okay, we have a x minus 1 cancels, so that means I have a hole at x equals 1. What's left on the bottom? X minus 5, so I know I have an asymptote at x equals 5. So the first step is to factor, see what's on the bottom, see anything cancels on top and bottom, and then we know where to go. So this is like a combination of the two examples we've already done. It has an asymptote at 5, x equals 5, so I know right here. Okay. I know over here I'm going to have 5. No work. I'm going to put VA for vertical asymptote. I'm going to pick some numbers less than 5. Let's say 3, 1, 0, and how about -5. And pick some numbers bigger. Now I picked this number deliberately here. What do you get when you plug in 1? Okay. That's going to be your hole. That's going to be your hole. Because when you plug in 1, you get an undefined in the original. So we'll have a hole wherever our graph is heading at x equals 1. Right around here, we're going to have a hole. And then just pick some other points, let's say just 6, 7, and 8. And then you'll have to crank out the answers for each one of these. Now you only need to plug these numbers into this simplified one. You don't have to plug it into the original. So like -5, we'll have to do -5 plus 1 and -5 minus 5, and we'll get -4 over -10, which is 2/5, which is 0.4. Okay. And then you'll have to plot them. So at -5, way over here, we're at 0.4. And you'll have to go through plug in 0. Plugging in 0 is pretty easy. You just end up with 1 over -5. Or -1/5, which is -0.2. And then you can kind of slowly get that pattern. You'll see the curve. But then right here at +1, you'll have that hole. And then I'll just continue as if nothing happened, and I'll go down here. And this will keep going closer and closer to that asymptote without actually reaching it. It doesn't go straight down, it curves slightly towards it. And then over here, I'll jump back up. Jump back up and slowly go towards it, like that. But yours will be more exact because you're going to have all these decimals. Okay. You're going to have all those decimals, but we'll have a hole right there. Undefined. Okay, so let's get you guys started on all this. Be able to answer these questions. When do you get a vertical asymptote? When do you get a hole? If you answer those two questions, you got it. Okay, so talk with someone next to you right now, answer those questions with each other, make sure you know when do you get a vertical asymptote, when do you get a hole, and then we'll go ahead and start the homework.